Hello everyone, welcome to Tux Riders and the third video of the FreeFEM series. In this video we want to have a look at the 3D mesh generation features of FreeFEM. Let's go for it. Okay, so in the previous video we had a look at 2D mesh generation features. And very similar to those examples that we saw in the previous episode, we have a couple of examples here for 3D mesh generation. FreeFEM has cool features for 3D mesh handling, modification, and generation, as well as adaptation that we will have a separate video for that, for mesh adaptation, I mean. But at the end of the day, a 3D mesh can be quite complex. So in the end, you may decide to import it from an external mesh. We have an example here. So like with Salumi, FreeCAD, or any other tool, you can generate a mesh and then import it in FreeFEM with all the labels and stuff. This is something that we have already discussed in Tux Riders, and we will have more in the future. But it doesn't necessarily mean that we don't need to generate some 3D geometries in FreeFEM. And it can have different applications, like for simple cases, for benchmarking, and also in parametric design of 3D geometries. It can be quite useful, the features that I want to show you in this video. So let's go to the examples one by one and run them together, similar to what we did in previous videos. So we start with the simplest form of 3D mesh generation and 3D geometry generation, that is actually with the cube function. So first of all, in order to work with mesh, with 3D mesh in FreeFEM, we need to load an external module. In this case, a plugin sort of, called MSH3. So for 2D, that was not necessary, and in this case, we need it. And then another package that I usually load is Medit, that is actually for working with a special file format, as well as a kind of built-in visualization tool, which can be called using a function Medit. And for that, we need to call this. We need to actually load these packages first. And the only difference, you will see this in this example, the only difference is with Medit is that it provides more information for visualization of geometries in comparison to the built-in plot function. So the cube function is very similar to the square function in 2D mesh, and in this case it accepts the mesh is the mesh size, so 20, 20, 40. These are the number of elements along each axis. And then again, as I said, similar to square, you have control on the location and the size of the mesh. So in this case, when you say size multiplied by x, size x multiplied by x, this is the size in the x direction, and similarly in y and z. So let me run this example. So in this case, I open a new terminal and I go to the folder. As I said in previous videos, you need to call FreeFEM and then the name of the file in the EDB format, and we usually pass v0 to that in order to suppress the, let's say, the output, program output, that is that contains also the source code of the program. So let me show you what I mean. Although we discussed this before, as you can see, I discussed this the mesh files later on, but you can see that it tells you a lot of things. So verbosity is not 0. In order to turn it off, to avoid printing the source code of the program as well as some additional information, we pass this argument to the program v0. It means that do not print any output. So in this case, this is a built-in Medit. This is the built-in plot function, and this is the Medit. Let's say visualizer. As you can see, we have a different size parameters along different directions In this case, you can see that along the z-axis this is more, and then the element numbers, the number of elements are defined also like this. So in embedded, you can have more features here for rendering mode and also for clipping that can be quite useful for us. But in the built-in editor, built-in visualization tool, these things are not supported. It's usually just pan, zoom, and plotting the finite element space and this kind of stuff. So let's make it more complex and a second example. Although this is not necessarily related to this video, this will be discussed later in the mesh adaptation video. So Tetgen is a great tool for mesh generation and also mesh adaptation. But I thought that it's worth mentioning in this video as well the way that you can generate some mesh files using Tetgen. That is, in the previous example, you saw that the mesh was structural, but in most of the cases, we don't want it to be like this, especially for more complex geometries. So in order to generate a mesh that is like, still the geometry is cuboid, let's say. And in this case, we want to have some unstructured tetrahedron mesh. So we pass the mesh to Tetgen Reconstruction with some parameters. These are very important parameters actually, but I don't want to discuss them. You can find the meaning of each letter here in the Tetgen documentation. But in this case, we want to generate a mesh. So we have the geometry, but we want to reconstruct the mesh such that it becomes according to the mesh size that we have. So you can see that the size of volume is something more or less approximated the size of tetrahedron, and then we can have like passing this parameter to the mesh that is already generation with a cube by the size of 2 by 2 by 2 only. But in the end, you will see that the mesh will be something like this. So example 2. And as you can see, now it starts to call, the Tetgen, but the mesh will be something like this. So as you can see, now it is very different. So all this mesh generation is something handled by Tetgen. And if I clip it, like toggle clip by pressing F1, it will be something like this. So I press F2 to modify the clip. And as you can see, this is actually the way that Tetgen has created a kind of unstructured mesh for us. So quite cool. Yeah, let's explore more functions that can be used for 3D mesh generation in FreeFEM. One of these functions is called move mesh to 3, and it means that we move a mesh from 2 dimension to the 3 dimension. The way that it works is based on creating a mesh, like we did all the things that we discussed for 2D mesh generation, in this case a square function for a simple square mesh, and then mapping it to 3D according to some function. So kind of, transforming the mesh based on some, parametric functions. In this case, you can see that we have the mesh S, so the surface mesh in FreeFEM. This is one of the fundamental types in FreeFEM. And then, using these 3 surfaces, we map, different aspects of the original mesh, and then we add them all together. So you can see that how FreeFEM allows you to, to deal with these kind of mesh entities. This freedom is highly appreciated when you want to deal with more complex problems and geometries, and this is quite nice. In addition to all the flexibility that you can have from an external program, this is quite interesting. And then, after generating the surface, after having the surface constructed, we pass it to Tetgen. Again, this is another another function, but as you can see, with more parameters here. So we want to have, ask Tetgen to reconstruct, to generate a mesh from a surface. So you can see that in this case, we have TH, another mesh that is generated and is type mesh 3. So 3D volumetric mesh generated from a surface mesh. So let's run this example together and see how it works. So Yeah, I call example 3 cylinder. And yeah, so this is the first mesh. This is 2D mesh that is generated based on, parametric design of a border, a geometry, and then generating mesh, as you can see with this size. And then, sorry, this is this size actually. And then having a square, a kind of square that maps it to, the 3D space. So this is the way that in the end it looks like. So this is, a quick way to generate a cylinder inside FreeFEM, although there are two other methods that we can generate such a mesh, but this is, one of them. So in the next example, we use another function that can be used for 3D mesh generation called build layers. Yeah, this one. And in this way, this is very similar, but then you have, a sort of a set of functions that can be passed, as transformation and also for bonding. And, it's more or less the same principle, but in this case, you have control in a way that, these mesh layers are constructed. Move from 2D to 3D, you have two different mesh files, and then you define the mappings and transformation. And in this case, you build a 3D mesh layer by layer. So similar to move mesh to 3, we need a 2D mesh. And then we define functions for transformation. In this case, this is a kind of, we add some trigonometric functions. And as a result, you can imagine that the final mesh is something that has a symmetry. So in this case, I call example 4. And yeah, so this is the 2D mesh. The original mesh that is designed with parametric 2D definition of geometries. And then we have this rotation. And as you can see, we have a very nice mesh here using the build layer function. So this is actually one cross section of this mesh. And then this is actually the way that it works. And then a very important function called trunk, and this example, generates a mesh similar to the example 4 using build mesh and build layers. But then I want to show you how this trunk function works. So in this case, at the end of this line, we have a mesh that is actually very similar to the previous example, a kind of cone like geometries. But then we want to generate, we want to create a hole in the middle of it. So in this case, we have a function that defines a kind of circle. And then we say the trunk to keep the regions that, in this case, you can see that the radius of the circle is more than something. So in this case, this is a kind of, this is this one actually. It's more than this is r squared. It's more than this. So in this case, this is very typical to write statements like this. So instead of saying that u equals this or is more than, 0.5, you say it like this, that the difference between u and 0.5 is more than a very small number, in order to avoid, some floating point operation errors, truncation error, and in this case, dealing with mesh sizes that some elements can fall outside of the region that you want to define, let's say. So in this case, after defining the mesh, we pass it to trunk, and then we generate another mesh, and then we plot them both, so you can see how it looks like. So example 5. So this is the original mesh. You see that I have weight equals 1 here. So this is the original mesh. As you can see, this is very similar to the mesh that we generated using build layer. In that case, that was a cone-like. This is more curvy. But then we pass it to trunk 0, kind of trunk. And then as you can see, we have something defined here that it's like when u is more than 0.5, so when it's actually square root of 0.5 is the radius of this circle. So, but if we refine a mesh, this is something that you can do yourself. We refine a mesh by changing the parameters of the mesh files here, and also this one. Then you will have finer mesh here, and as a result, a more precise circle being clipped or being trimmed, or in this case truncated from the original mesh. This function can be used also in combination with external mesh files, so that you can modify some regions of the mesh that you don't need, or you want to keep, or you want to, in some cases, you want to split a mesh. And the function works both in 2D and 3D, and this is a very powerful actually function. And then for the surface, this is an example that you already saw in the cylinder example, but in this case it is less complex. So all the essential steps are here, and that's actually again related to the mesh S. So a surface, creating a surface using square 3D. So that's a kind of 3D, a 2D entity in 3D space. So square 3D is a function that generates something like that. As you can see, it accepts only 2 parameters, and then it returns a surface. And then this surface is defined using the functions that actually define it. And then we print the number of elements of this surface, as you can see here, and also the boundary elements. And we pass it to Tetgen with some parameters that are used for 3D mesh generation instead of for adaptation and stuff. And then in the end we plot it. So let's run example 8 together. Example 6, sorry. So in this case, example 6, and yeah. So this is a kind of donut volume, donut shaped volume, and initially it was a surface, and then using Tetgen we have a volume mesh out of it that can be used to to solve some stuff. So for these kind of elements that you can define parametrically, you don't really need to import the mesh from an external program. And then, the example 7 is related, again, similar to the example 2. This is related to mesh adaptation. So we come back to MMG. MMG is a very powerful mesh, let's say, manipulation tool, a mesh generation tool that has nicely integrated in FreeFEM by FreeFEM developers. And we use it a lot in Tux Riders. In this case, I want to use it for mesh generation, so for complex mesh, for complex geometries, sort of, that can be defined again parametrically. In this case, it's a kind of doll or Pinocchio kind of, a Pinocchio head that has a big nose. And for doing that, all the some of the elements of the face, of the head, of the doll are defined as functions. In this case, head and 2 ears and nose. And then we define a finite element space on it. This is something that we will discuss in the next video, so I don't want to emphasize, I don't want to go to the details of this function, of what this means. But for now, just imagine that this is a kind of mapping from these functions to the finite element mesh. And this type of notation for minimum of these two, and then minimum of the results to that, and then minimum of the whole results to the nose, is just to define the function that forms the head inside the cube, inside the mesh, 3D mesh that we have. So in this way, we manage to have the value of 1 inside or outside of the face, and a value of 0 inside it. And then, this finite element space is passed to MMG3D. That is a very powerful interface. In the future, you will see that we use this interface a lot in Tux Riders, even for creating complex geometries that we don't want to necessarily simulate in FreeFEM, but we want to have the geometries like for 3D printing and those kind of stuff, those kind of applications, even using this level set splitting available in MMG3D. But in this case, I just want to emphasize the application that can be used for 3D mesh generation. And then using that mesh, we split it based on, build a BD mesh function. So after generating the 3D mesh, we have like a BD function, and when defined, we extract again using the trunc function the region that is 10. This is a value that is defined by the MMG function for the level set of splitting. And then we have, like, again, we remesh it. We remesh it again using MMG, this time MMGS, which is a surface mesh generator of MMG, and then we plot it using medit. So let's see how it looks like. This is very cool. As I said, this is just one example that later on we will have. I will show you more applications of MMG inside FreeFEM. So this is a typical output of MMG for people who have used it. And we had actually, a video on installing MMG for compiling MMG from source codes. And then, so this is, that was actually the first mesh. So the first thing that you saw was actually the original mesh that was here. So internally that was adapted. But in this case, after extracting the level set separation or splitting a mesh, we have something like this. This is actually a surface mesh, but can be, how to go back from a surface mesh to a volume mesh. So as you can see, this is super nice, the way that you can work with these kind of functions. But as I said, in mesh adaptation video, I will show you more examples. So just to show you that, the mesh that we saw in the first plot is actually something that is internally adapted to these functions. And then, here is what we see, but, just sort of surface, the external view of the mesh. But internally, I press F1. Internally, we see something like this. As you can see, this is a kind of level set splitting that is nicely plotted using MMG. And so this is what MMG does actually. And then after we split it using the trunc function, it becomes something like this. But yeah, we will see more examples in the future from these functions. A lot of projects that we do in TuxWriters are based on this kind of mesh adaptation. And then the last example, which is similar to the previous video for 2D mesh, is based on an external mesh. Loading external mesh inside FreeFEM. As I said, this is something that probably has the most applications in FreeFEM, because it gives you freedom to design your mesh inside a more sophisticated CAD tool or mesh generator, and load it inside FreeFEM. So what we need is actually just loading the package for 3D mesh and then read it using red mesh 3. So for 2D mesh, it was red mesh, and for 3D mesh, it is red mesh 3. And we load this mesh that is inside the mesh directory here, and we plot mesh. So let me run this example 8, and load external mesh. So yeah, this is the mesh that has also some internal faces, as you can see here. And this is something that can be, as I said, super easy to import mesh inside FreeFEM. So as you can see, we have different colors for the labels. Red for the wall. This is a kind of for CFD simulation, that kind of concentration or heat is released from this internal surface. So the wall for the surroundings, and then internal obstacle with yellow, showing that it has another label, and then for the inlet and outlet, as you can see, they're orange. So different colors for different labels. So yeah, these were some examples that I wanted to show you for 3D mesh generation in FreeFEM. I hope you find it useful, and you can find a link to the source codes in the description of the video. You can download the codes and run them yourself, trying to modify the parameters and play with them. I hope you find this useful, enjoy it, and see you in next videos. Bye.